My name is Stan Zachary. I'm one of the organisers, and I'm chairing this afternoon's session. Right, somewhat experimental week. We're trying to explore the extent to which mathematicians can help with energy research. This has not tended to be something in the past. Energy systems in the future are very much different. There's very much more uncertainty, much more volatility, and also very much more controllability. And of course, a feature of recent years has been the liberalisation of the electricity market. We no longer have a single centralised supplier. And so something of particular interest to mathematicians is how to make the entire system how it ought to work well, and how to incentivise individual players in the market who may be presumed to be acting in the interest of self-interest, the suppliers, the grid operators, and so on, how to regulate that so that they play in a way that works for the benefit of the entire system. So there are these various themes. They're all fairly new themes, and this is a little experimental. This afternoon and tomorrow morning, afternoon, Wednesday morning, we're having various tutorial sessions from people, engineers, mathematicians, economists, who are already working in these areas. And so we are starting this afternoon with a double act from Benjamin Hobbs from Johns Hopkins University, who's a mathematician and economist, who is spending a year in Cambridge, I think primarily at the Energy Policy Research Group. Is that right, Ben? And Danny Ralph, who's an economist and mathematician again, or operations research, who is based at the Judge Institute here in Cambridge. Okay, so they are going to do it between them for 2 sessions, and I think Ben is going to start, and I'll hand over now to him.
Thanks very much. Thanks to the organizers, Chris, Stan, everybody else. My goal this afternoon is to get some basic vocabulary and concepts down that the folks in the next few days will then build upon in terms of showing you real state-of-the-art type of mathematics, the sorts of problems that we need your help with. What I'll do first is try to say why power is so interesting compared to other commodities. Why is it more interesting than rapeseed oil, for example, as a sector to study, as a sector to apply mathematics to? I'll define the type of models I'm interested in, which are engineering economic Bono-type models, and some of their uses within the industry and by policymakers. I'm more on the economic side of this economic/mathematician hybrid Stan mentioned. Danny is more on the mathematics side. I love working with mathematicians because they can prove things that utterly surprise me. They can come up with algorithms to solve what I think are impossible problems, and he's been a great person to work with this year. I'm more of a modeler. I state the problem in mathematics terms and then scratch my head and look for somebody like Danny to help me out. After that general introduction, I'm going to show 5 very basic type of problems that you'll see in various forms this week. Problems that deal with operations, how you operate your generators moment to moment, maybe how we make the grid a little bit smarter by getting demand to respond to prices. These gentlemen here, these fine gentlemen here, are standing under the first AC power line in the world. The basic technology today is the same as what they use in terms of how to control the grid. Well, we don't use horses anymore, but control the grid basically emphasizes the supply side, getting generators to go up and down as demand varies up and down. That's what I call the dumb grid. We want to make the grid smart. We want to be able to control transmission better, for example, by switching things, and we want to get demand to play as well and be an equal partner. So I'll talk a little bit about a demand response model. Add some dynamics, something called unit commitment, where instead of dispatching moment to moment, you're looking over, say, the next day and saying, you know, which power plant should I turn the key on and start up, and which one should I shut down and when? Then I'll talk about one thing that makes power very different, that's transmission and how it's modeled. And finally, look at some long-term investment problems called capacity expansion. So first of all, 4 reasons why power is perhaps more interesting than rapeseed oil. And one is its economic impact. It's similar to this in terms of the size of the economy to oil. It's twice as large as the higher education sector, which wounds my heart. 10 times as big as the water resources sector. About half of U.S. energy use is through electricity, and is also the most capital-intensive economic sector. So that means you invest in stuff and it's around for a long time. You build a nuclear power plant today, you're going to be dealing with it in 50 years. Second, when the system is broken, the whole economy feels it. I don't know how many of you are old enough to remember Arthur Scargill. At least there was one hand here who led a disastrous coal strike in the UK in the 1970s, which paved the way for the Labour government to be defeated and Margaret Thatcher then to be elected. And the economy shrunk by a significant percentage. Experienced the same thing in California in 2000, 2001. And if you've ever lived in the third world as I have in West Africa, you know that economic activity and actually social welfare is significantly impacted by chronic shortages. And finally, it's of particular interest now because of something that Margaret and Fred did, 1978 or so. Margaret being, of course, Margaret Thatcher. She basically said, there's no alternative, we've got to privatize. She was looking for some family silver to sell, and she sold off the power sector without necessarily the benefit of mathematicians and economic theorists helping her to tell her how to do it, sheer force of will. At the same time, Fred Schweppe, an MIT electrical engineer, had this vision of a power system where everybody is coordinated by price. So you see a price and you say, is this a good time to do the wash or not? Or to melt some aluminum ingots. And later occurred to him, we can not only coordinate demand, we could coordinate supply by sending prices to power plants. And his models are the intellectual underpinnings of restructuring throughout the world today. As a result of political will and some great ideas, we've seen a lot of changes in the industry structurally, vertical disintegration, separating generation from transmission from distribution, so that transmission is freely accessible to all and generators compete against each other. The creation of spot and forward markets, and then subsequently we've had both horizontal disintegration. That is, for example, in the UK, we started out with 2 big power companies and they were gradually broken up. But we've also had cross-country mergers, and these all have important implications for competition that I don't think we fully understand. Okay, economics. There's the polar bears, environmental impacts. We've had huge transitions over time in the power industry. And we're going to see some huge transitions in the future if we really are going to accomplish the goal by 2050 of wringing carbon out of the economy. We've got to go from a coal-based economy, natural gas-based electricity system to something based in renewables, perhaps nuclear, perhaps fusion. We'll see. At any rate, open the newspaper at any time, you're going to see environmental controversies over transmission lines or wind towers, what have you, destroying the landscape. Most of the sulfur dioxide that causes acid rain comes from power plants, at least in the United States. 1/3 of the nitrogen oxides that cause urban smog come from power plants. About 40% of the carbon dioxide that contributes to the greenhouse effect, at least in the US, comes from power plants. And if we don't do anything, this will increase by about 50%, at least in the US, by the year 2025, because we have been on a path of using a lot more coal because it's the cheapest fuel. Nuclear has been stagnant, natural gas hasn't been going anywhere, renewables have been sort of nudging up a little bit. So if we don't change policy, it's going to be a lot harder to wring carbon out of this system than out of this system. Okay, so economy, environment. The third interesting aspect about this compared to rapeseed oil is that power is the ultimate just-in-time product. It's difficult to store. It is possible to store in some cases, but it's very expensive. So generally, you have to balance supply and demand in real time, not necessarily second to second, because there's some inertia in large power plants. So if suddenly I switch on a light, then power plants throughout the UK will start to slow down. There'll be an energy transfer. But we've got to speed them back up again because we want to maintain 50 hertz. So within seconds or minutes, we've got to keep supply and demand balanced. Now, when that happens, as Sean Menn is going to be showing you later this week, you get huge price volatility, far more than you see in other markets. So this might be the price of oil over the last 30 years. Instead, it's the price of electric power in a 24-hour period, very typical 24-hour period, in the market that I call home, Pennsylvania, Jersey, Maryland. So a tenfold difference over 10 hours between the time that everybody's got their air conditioners on and the time that, well, before everybody's gotten up in the morning. If we look at this pattern over the course of several years, you get some really remarkable spikes. Let's see, that goes up to $1,000 per megawatt hour, which compared to the lowest levels is 2 orders of magnitude. That does not happen in rapeseed oil, nor in any other commodity over this time scale. Okay, so let's see. Economics, environment, volatility. The fourth reason is that we've got some really interesting technical problems. Remember those gentlemen with their horse? There's a lot of technology change that's needed, that we need to catch up with to make grids smart. Here's the challenge. The challenge is that there are 3 large machines, basically, that cover all of North America. That standing in Maine, I am vibrating at the same frequency that somebody in Key West, Florida, or in Chicago is vibrating at. We're all connected together. And what that means is what I do in Maine affects, maybe just a little bit, but affects everybody everywhere else in eastern North America, the eastern interconnection. So we have to carefully control the system to make sure it doesn't collapse the way it did in August 2003, for example. So an example of what I do affecting everybody else, if I decide to buy some power in the western US and ship it east, it will follow all parallel paths between Chicago, say, and New York, perhaps congesting somebody else's transmission lines, making them overloaded and they have to do something. What you do affects everyone else, and that makes it a hard system to control. The networks have no valves. This is not like oil pipelines or natural gas pipelines where you can close a valve and redirect power one way or the other. It follows all parallel paths according to Kirchhoff's laws. And the final technical challenge is that St. Fred, I've added Saint to the beginning of his name, Fred Schweppe from MIT, his dream of an active demand side where we're all helping to manage the grid and making money while we do it, remains just that, a dream. We have a broken demand side of the market, which makes the market easier to exploit if you're a monopoly and large producer, and makes it harder to control, and we've got to fix that. So all sorts of interesting mathematical problems, not only interesting in and of themselves, but societally very important. Okay, item 2, some model definitions. What do I mean by model? Well, I could be talking about statistical models, but I'm not. I'm going to talk about bottom-up engineering economic models. Basically, any models that simulate or optimize the short-term operation control or long-term investment and planning of generation, transmission, and use of power, considering environmental impacts, costs, other societal impacts, using mathematics, definitely, and sometimes computers. Sometimes the most useful models, and this will warm your hearts, sometimes the most useful models are ones you can get closed form results for and prove general theorems for. That's actually been important in my work as a market monitor, as I'll explain a little bit later. But we also need really big models as well, as I'll explain. I focus not on statistical models, but bottom-up or process engineering models, which explicitly represent the technical components, the texture of a real system, real power plants you can stub your toe against, real transmission lines. These type of models, optimization models or math programming models as they're called, are used by companies for their operations and investment decisions, but they're also used by policy analysts such as myself to try to figure out how a market might respond if I change, for example, an environmental policy, I cap CO2, or if I give subsidies for renewable energy. How much more will I see? The elements of these models, to those of you who've taught any optimization, this is very familiar. We've got decision variables, the things you can yank and move around, either design or control. We've got an objective function that will just tell us whether a solution is a good one or not. For example, we might be trying to maximize profit. And finally, we got constraints that define a feasible region. If you're lucky, this is a convex feasible region, which enables us to prove all sorts of properties. But in the real world, it's highly non-convex, unfortunately. Things like mass balances, limits to capacity of power plants and transmission, rules that say there's certain places you can't build stuff or you can't emit more than a certain amount of pollution, requirements that you build enough capacity to meet reliability requirements of the grid. For example, having a 15% extra capacity so you can meet demand. The responsibilities for decisions about controlling and building the grid are scattered among all sorts of levels in the supply chain, from those who provide the fuel, gas, coal, nuclear fuel, etc., to those who own the power plants, to the grid operator and the low voltage distribution operator. Those are usually separate companies, at least in the UK and the US. Something that you all call suppliers here in the UK, we call marketers. These are the people who go out and buy power and then turn around and sell it to the consumers. And they may have nothing but a computer on their desk. And finally, the consumers themselves. They each have problems that require mathematics to solve them. And so let's talk about some of those problems. First, let's talk about control. And we'll start with very short time scale and move to a longer time scale. So automatic protection. Instead of an operator moving levers, you've got an automatic generation control system. So if it detects a change in frequency, for example, decreasing frequency, it automatically adds more fuel to certain power plants. Or it may open up breakers to protect equipment if it detects an abnormal flow or abnormal voltage. This is usually the responsibility of the transmission system operator. Little longer time scale, a few minutes. Dispatching of plants. You can manually move plants up and down as demand grows at the beginning of the day or goes down at the end of the day. And you have to be mindful of technical constraints in the grids. Dispatch can be done centrally by the transmission system operator, as it was done by the pool system that Margaret Thatcher established. Or it might be done on a more decentralized basis by generation owners, which is the system you now have in the United Kingdom, where people decide what power plants to operate and send a schedule. Okay, now let's move from minutes to hours to maybe a week, something called unit commitment. We have to decide which generators to turn on. We've got a coal power plant here. Do we heat it up and run it, or do we buy power from somewhere else? And we are either minimizing costs, maximizing profits. We might have something called operating reserve constraints because we have to guard against contingencies. Power plants might go down. What caused the big blackout in New York City in 1977 were lucky strikes or unlucky strikes. 2 transmission lines were hit by lightning. You have to keep extra capacity around, sort of on its toes, to be ready to react. That's called preventive protection or preventive control before the contingency happens, so you can react. So that's a concern in unit commitment. Maintenance and production scheduling, for example, your nuclear power plants have to be refueled every 3 to 5 years. When's the best time to do it? Well, usually a cool but not cold time of year when demands are low. Okay, from control to investment to system design, we have design problems for consumers. What energy-using equipment are we going to use? And power companies worry about this because they would like consumers to use less. Power that's not consumed doesn't have to be supplied. Transmission and distribution planning, which we'll see an example of in the next hour. where we decide what transmission lines should be built where and when, and then something called resource planning in the long term, what new types of power plants should be built. And there's a big debate now in the UK about, for example, whether there should be new nuclear plants or not. You've got this interesting coalition between the Conservatives and the Lib Dems. The Lib Dems have been wholeheartedly against nuclear power. The Conservatives think it's okay, but as long as you give local people the right to control land use planning decisions. It's not clear how this is going to work out, whether we'll see new nuclear plants here or not. So that's a multi-decadal time scale. Okay, other sorts of decisions, pricing decisions. For example, if you own a power plant, you might want to bid into market, and you have to figure out, okay, what price should I be willing to accept? I want to submit some offers to sell my energy or maybe sell my spare capacity. And then pricing decisions on the other side, they're the folks who clear the market. They use very large-scale optimization models, tens of millions of variables sometimes, to clear the market, to take all the bids from the different generators and consumers and to figure out which power plant should be operated when. This software costs about $100 million a shot. So it's not something, unfortunately, I can demonstrate here on my laptop. Okay, policy uses of this stuff. The previous applications are emphasizing models that have sort of single objective. You're maximizing profit or minimizing cost from a single entity's point of view. Now let's step back. You're a policymaker who works for, say, the U.S. Environmental Protection Agency. You're considering some new rule limiting maybe mercury out of the smokestacks of power plants, and you wonder, how will the market respond? What will happen to the price of power? Do we risk any shortages? What will happen to other pollutants if I really tighten up on mercury? To do that, we take these models that individual firms use and we collect them together to make market models. And there are two approaches to this. One is, the second bullet here, is take each market player's optimization problem, take its first order conditions, Kuhn-Tucker conditions. So you got first order conditions for every one of these optimization models, pile them up in the middle of the table, then impose the condition that supply equals demand. That's called market clearing. It's sort of a ribbon to wrap these all together. If you're lucky, you'll have n conditions and n unknowns that you'll be able to solve with the sort of software that Danny has been involved in creating. So, in other words, attack the equilibrium conditions directly, find the values of the n variables that solve that n unknowns. The equilibrium being the situation where nobody wants to change what they do. They're all thinking they're maximizing their profit subject to the prices they see in the market. That's one approach. Another approach, if you're lucky, you've got that pile of first order conditions and market clearing conditions. There is sometimes a single optimization model whose first order conditions are identical to that, which means that under appropriate convexity conditions and so forth, if you can solve this one model, you get a solution that also satisfies equilibrium conditions, and you've got an equilibrium. That's kind of cool. It's as if there's somebody's invisible hand guiding the entire market towards some objective. Paul Samuelson, Nobel Prize winner, pointed out that if we're simulating a perfectly competitive market where nobody believes they can manipulate the price, we can simulate that by maximizing the sum of producer surplus, a fancy way of saying profit, plus consumer surplus, which is a fancy way of saying net benefits to consumers. In other words, maximize net benefits to everybody. It gives you the perfectly competitive market solution. A cool result. Of course, you have to believe a few assumptions to use that. But it's a good first place to start. Okay, and the use of this stuff, again, I asked the question, what are the impacts of policy change on stuff that policymakers and the public care about? Cost of power, emissions, and so forth. Okay, the structure of these things is kind of like this. In the case of a market model, we start with a single firm. Maybe it's just its control decisions. Maybe it's also long-term investment decisions. And we have models of all the other entities. We have a model of the demand side. How do consumers react to prices? We might have a model of the operation of the transmission grid as well. I don't show that here. We have the market clearing conditions, supply equals demand, that ties us all together. And if you're lucky, you have n conditions and n unknowns. It's a competitive model if everybody assumes they can't affect the price. No matter what I do, the price is the same. Highly naive. If instead, every market player assumes that others won't change the amount they sell. So if I'm a coal company and Chris is one who owns some natural gas plants, if I decide how much power to produce, assuming he won't change the megawatts he produces, I'll then think, okay, if I produce less, I can force price up. I can squeeze the market. He'll think the same thing, and you can define an equilibrium in this game, which is called a Nash-Cournot game. It's a Nash game meaning that everybody, in a sense, assumes that other folks won't change their strategies, and it's a Cournot game because the strategy is quantity. So here's a really important question. What did John Nash's father do for a living? Anybody know? It's actually, so a hint, that actually is relevant here. Okay. He was an electric power engineer for America's largest power company. So that's somehow appropriate. Okay, to close up the introduction to models, you've all heard this cliche before. Every model is wrong, but nevertheless some are useful. The small ones are useful if you're in a situation where it's Thursday, the CEO calls you up and says, we have an opportunity to make a deal by Monday. Or, there's a public hearing on Tuesday on this proposal. What is the position that we should take on it? And what you need in that circumstance are simple models whose relationship to the assumptions is very transparent. Anybody can follow it. These models are a way to tell a story and then can be used to derive general conclusions. So in my role as I'm on the California Market Surveillance Committee, we often get the situation where there's a proposal one week. For example, there was a proposal for personal carbon trading cards. This idea of power plants trading emissions was ridiculous, somebody said. They said, let's give everybody in the audience here a credit card. And so when you buy something, for example, hot dogs from a hot dog vendor, you pay them money and you pay them carbon credits. And then we'll give everybody a carbon budget. And that's how we'll get people's carbon emissions down. So this was going to be discussed at a hearing in 2 weeks. There's no way it could put together a large computational model to investigate this. So instead you put together a small model and you try to prove some things. See if you can prove anything. And what I was able to show was that that proposal was dominated by having power plants trade, because the personal credit card proposal would be at least as expensive and probably much more expensive because of transaction costs than just having power plants do it, that there was no economic advantage. So small, transparent models are useful in that sort of thing. People then can look at the assumptions and critique them. On the other hand, we need to keep the lights on minute to minute. So that means we need that $100 million software to come up with particular numbers, which power plants are going to be operated when. And then in between, for policy analysis of the sort that, for example, the U.S. Environmental Protection Agency does, you need models that have some realistic detail, that can tell the difference between different types of power plants and different locations, but they don't take all day to run, so you can do sensitivity analysis. So we need folks who can do analysis at the top. We need folks who can compute very large problems in the middle, and then maybe sort of both in between there. So we need mathematicians for all those roles. So what I'd like to do now, that I hope I've convinced you, or at least make you think it's possible that power is more interesting than rapeseed, I would like to show some very popular types of models. These are extremely simple, and you'll see much more complex versions of these models as the week goes on. Hopefully, having seen the simple ones now, when you see it again, you'll say, oh yeah, I remember the structure of this and what it's trying to do, and it will be helpful in appreciating what happens later in the week. So I'm going to start with a simple operations model where I'm actually trying to figure out what's the best way to operate a power system if I have some power plants. And I'm going to ignore transmission. I'm going to ignore the sort of constraints like the cost of starting up power plants and so forth. I will have a single decision variable G, which represents the level of operation of a generator. I'm going to slap on a couple of subscripts on that. So this might be time, for example, T equal 1 through 8760 hours per year. And this might be the index for different plants or different locations or something else. So megawatts is the units that we usually work with. And so we have peak periods, off-peak periods, nuclear plants, gas plants, coal plants, wind plants. Got a bunch of coefficients. I don't need to go through these too carefully because I think when you see the next slide, you'll see the structure of the model. But you have to come up with costs. You have to adjust for the length of different times, capacity constraints. You have to shut plants down some of the time, either because you don't have enough water to run them, or you have to do maintenance. So there might be a maximum fraction of the time that you can operate them. And finally, there's the demand that needs to be met. So this is a dumb grid. I'm going to assume that demand is fixed. We aren't fulfilling St. Fred's vision. In any optimization model, math program, you have an objective function, decision variables, and constraints. What we are optimizing, the objective function, we're pushing that as low as possible, is the total variable costs. Some plants are cheap to run, some are expensive. G is our decision variable, what we move around. CG is the cost per unit, and HT is something to adjust for the number of hours. Something prevents us from getting negative infinity, and those are the constraints. We have to choose values of G from within a feasible region. We have to meet demand. We can't exceed capacity, except very temporary basis. The total energy produced over the year can't be more than the capacity allowed, adjusting for maintenance, adjusting for the amount of water, for example, and then non-negativity. So there's some, in this case, it's a polyhedral set in a linear program. We want to find the values of G within that set that minimize that. And those of you who have studied linear programs know that there are some really nice features of linear programs, that the feasible region is polyhedral, and some extreme point is an optimal solution. So you just need to look at the extreme points, and we have software that can solve this for tens of millions of variables. Not on a laptop. You can solve 1 million variables on a laptop, and we'll see an example later today. So here's an example. And I'd like you to turn to your neighbor and see if you can figure out what the answer to this one is. All right? And then we'll come back in a couple minutes. You've got 2 power plants. A peaker, which is really expensive to run, 70 quid per megawatt hour, and it's a moderate-sized plant, about 800 megawatts. And then we have a bigger plant that is really cheap to run. Okay? We have 2 demand periods. We have a peak period that's 2,200, is that right? No, 760 hours per year. So if I arrange demand in decreasing order from peak demand to off-peak demand, if you actually did it, you'd get a distribution like this. It's actually a cumulative distribution demand. And I'm going to approximate that as 2 periods that look like this, 760, and then 8760. So this is the peak period, off-peak. Peak demand is 2,200. Off-peak demand is 1,300. Okay, so the question is, well, don't write down the linear program. This is what I make the class do. But tell me, just by looking at this, can you figure out what must be the best solution? Which power plants do you operate when? So can you Oh, let's not do the hydro plant. That makes it more interesting. Okay, so turn to your neighbor. Let's take a couple of minutes. Just see, can you tell me which power plants you'll operate when? And if you're bored, solve that problem as well.
Hey, you haven't given us one. Yeah, you can't solve that. How low can you run these plants? Do you have to run the base load generator?
Yeah, let's assume you can turn it down to 0, which is not necessarily the case.
But you can choose anywhere in between.
Anywhere between 0 and 800 for the peaker, between 0 and 1500 for the base plant. Good question.
You can't solve the hydro plants.
Hydro plant is no fuel cost.
Yes.
Just the slicing and dicing of fish that go through the turbine. We're going to disregard that. So let me give you 45 seconds, and then I'll see if anybody has an answer. Okay. So let's look at each of these. If I wrote this down as a linear program, it would look like this. I had 4 variables. In each of the 2 periods, I have 2 plants to operate. So I might, operate my base load, my coal plant here, and my coal plant there, and then my peaker might be these or something. So they're 2 by 2, 4 possibilities. And demand constraints, capacity constraints. So this has a particular structure, which is, since you're only meeting demand and there's only a capacity limit, you should use what's called the greedy algorithm. Use the cheapest plant first, which means you use the coal plant as much as you can in each of these 2 periods. You have 1,500 capacity for the coal plant, and then use the more expensive plant, the $70 plant, only if you have to. So that's a very simple problem to solve. I hope you all got that answer. Yes? Okay.
Example of linear programming, was it? Because that was so intuitive that you wouldn't write down the equations, you just know the answer.
Yes. So it is a linear program, but the solution is a very, very simple, straightforward one. Now, we start adding complications such as transmission or hydropower, it becomes a little less intuitive. So if I add hydropower, so I have a 100 megawatt hydro plant whose output is limited in each period, which can contribute to demand in each period, but has this limit. You only have so much water behind the plant. You can't operate it flat out for the entire year, even though it's free. You have only about enough water to produce maybe 30%. This is perhaps 30% of what it could produce if you had no water limitation. And so now we're coupling the periods. Now the greedy algorithm isn't quite so good, because the greedy algorithm would say use the cheapest one, which is hydro, first in each period. Well, that's not true, because you only have so much water. You want to use it in the peak period when you can save on the gas costs. You don't want to use it here when all you're saving is coal costs. And this requires that you consider both periods at once. So I've thrown in a constraint. Let's see. If you look at this problem, except for this problem is separable in time. You can solve it separately for peak and off-peak by the greedy algorithm. Now I've coupled it over time, and it's going to take a little while longer to solve. Now, real problems like this can be a million or several million variables, because we have with the California system, something like 500 power plants and 4,000 transmission lines. And we're operating at over half-hour periods over the next 24 hours. So we're easily up into, especially when you start considering contingencies. How does the system adjust if a power line goes out? We're up into the millions and millions of variables. Coupling over time and coupling over space. So, okay. But we've done a simple dispatch problem, and you'll see much more complicated ones later this week, including from Daniel Kirshner. I just saw Daniel walk in. You'll see some very, very fancy ones later from him. Okay, now, as I said, this is a dumb grid. We're back in the horse and buggy age, as I showed you in my first slide, in terms of ignoring the role of demand in markets, that we've emphasized sophisticated control of the supply side, generally to the detriment of demand. Now, that's not completely fair. Daniel's written a whole book on the demand side, which I heartily commend you, right? What's the title of it? Don't be shy.
Not just the demand.
Oh, sorry. Well, you've written one on economics, but wasn't there a jointly authored one also on demand side stuff? Ah, sorry. Okay, that was somebody else.
Good suggestion, though.
Yeah, okay. Conceptually, we're starting getting some of the tools in place. We're starting some small-scale experiments. So what if, for example, each of us would see the price light up in the kitchen, or had some other way of knowing what the price of electricity was, and either we react to it ourselves, or, which is more likely, we have little microprocessors reacting to it, so that if the price is high, our hot water heater goes off, or our laundry is delayed, or what have you. We can simulate that with a model like this. I have a new variable, which is the level of demand. It's now variable, it's not fixed. And I have a new term in the objective function, which is the integral of the inverse demand curve. This is not probability, but this is price. And this is quantity consumed. And economists assume that demand is downward sloping, that the first cappuccino you have in the morning, you drink in the morning, is more valuable than the second and the third and so forth. And if you consume 10 cappuccinos, which I don't do too often except when preparing lectures like this, the total benefit you get is the integral of this thing, which will come out to dollars, is the integral of the inverse demand curve. And that's what you see here. And this is a common way of simulating smart grids in which consumers are induced to do stuff, like go without a cappuccino, move around when they do their laundry, change their industrial processes. They're induced to do stuff through the price mechanism. There are other ways to control the demand side as well that I won't talk about. But this is a small step in the direction of a smarter grid. It's not a smart grid yet, but a smarter grid, in that we're now getting demand involved in balancing the system. When supply conditions are such that you are really short of capacity or a line goes out, you can have demand help you out. Okay, well, that was quick. That's all I have to say on demand response at this point. Let's now put in some dynamics. Unit commitment. Which power plants do I turn on, and which ones do I turn off? It can take hours and hours for the big coal plants to be first turned on from a cold state, have their boilers heated up and so forth, to being fully online and providing power. So if you have high demand right now, that power plant's not going to do you any good if it's offline, and you have to plan ahead to have it online. So we're moving from a linear program now. I should have said, if P is linear, then the integral is quadratic. So we're out of a linear programming world. We're now in something called quadratic programming. We have a nonlinear objective, which is, if we're maximizing this, we're hoping this is a nice concave function. There's certain nice properties about that. But we're still these are still nice. This, however, is not nice, NP hard. We've got 0-1 decisions to decide which power plants to turn on and which ones to turn off. And that makes this a much more difficult problem. These U variables, 1 if it's on, 0 if it's off, you're either pregnant or not pregnant, there's nothing in between. Cost for that. You have minimum run levels. If you turn it on, you have to operate at a certain level. If you operate below that level, the flames, might have flame stability problems. You don't want your power plants blowing up. I'm going to take these time periods, and instead of arranging them in decreasing order of demand, I'm going to make it chronologic. So we have demand now varying like this from day to day. Because now we're scheduling when to turn on plants. If we want the plant available here, we've got to turn it on here, perhaps. And then finally, ramp rates. Plants can only move so fast. They can't change very quickly. That's going to be an increasing problem as we have more wind energy, which Mark O'Malley will tell you about on Wednesday morning, about some of the problems that causes on power systems. If you have a lot of wind, that means you have to have a lot of flexible thermal capacity, just ready to move in case the wind drops off or picks up. But that thermal capacity can only move so fast. So the model is then modified as follows. We have costs for turning on the plant, costs for running it at a minimum run level. In addition, the costs associated with that we model as being associated with energy output. I've added the following constraints. This is the same, generation equals demand. Now I have a lower bound on G. Well, we don't need this anymore. We have a lower bound on G that's basically the minimum run level times 1 if you've decided to turn it on. And then we have ramp rates that tell you that the difference over time can't be more than a certain amount. Let's see. I guess the others really aren't very important. And this is the nightmarish thing. Well, a couple of these aren't bad, a couple of binary variables. But in California, we're trying to solve problems where we have hundreds of binary variables per hour. We're solving it 24 hours ahead of time. This in a nonlinear system with thousands of transmission lines and so forth. This becomes a very difficult problem to solve to optimality. And in fact, the dirty truth is that we don't solve it to optimality. We sort of get within 2%. We say, well, it's probably close enough. Don't tell the market parties, because people get upset if they realize you're not solving it all the way to optimality. They say, you didn't choose my plant because you didn't go to optimality. So that's a real problem. Okay, so that's a little bit more complicated because now we're dynamic. And now we've got lumpy variables. That definitely makes the problem more difficult. Because we've added time periods, the problem's gotten a lot bigger. Because we've added binary variables, the problem's got more difficult to solve. And if you're not familiar with optimization software and you're wondering, how you might use a gradient method to solve a problem with 0, 1 variables, Danny Boy is the guy to ask. No.
Don't use gradients for 0, 1 variables unless you're... No, I won't go any further.
Say that again?
No, yes, we can talk about that later.
Okay. All right. So, disposed with unit commitment, demand response, dispatch. Let's talk about transmission. What really makes electricity different from rapeseed oil? So this, you may remember your freshman physics, or fresher physics, I guess you say in this country. Things like Ohm's law that says, the current flow from one point to another is proportional to the voltage difference, accounting for the resistance. And current law that says that current can't be created or electrons can't be created or destroyed. The net flow of electrons into a point has to equal 0. And Kirchhoff's voltage law. We have no valves in this system. And so if you have a system that's a circuit and you look at the voltage differences around that circuit, if you start at VB, you have to end at VB. So this voltage difference plus this one have to add up to 0. And then substituting in Ohm's law from the top, that means we have this equality restriction on currents that has to be satisfied instantaneously. I know electrical engineers such as Daniel get really nervous when they see the comments like me talking about Kirchhoff's laws. I mean, did I even spell his name right, 2 H's? Okay. All right. There's some interesting implications of these laws for the physics and for the economics. you can use those simple equations to calculate stuff that we're interested in particular to calculate load flow. If we know how much stuff is coming into the network from generators, and we know how much stuff the consumers are taking out, we take those laws in the previous overhead, plus we need I squared R, we need resistance losses. Put them all together, we'll be able to solve for the flow on each line plus the net injection at something I call the swing bus, because we don't know ahead of time how much losses we have. That's called the load flow problem. And we're going to hear a lot about that later this week from Daniel, right? Okay. There's some very odd consequences of this. There are no valves in this network. You can't direct it. So if you produce in one place and selling power to another, it follows all parallel flows. So if you produce power in Germany and sell it to the Netherlands, a significant fraction of it goes through France, perhaps causing problems for the French system. Well, there are some advanced electronics, things called FACS devices, flexible AC transmission devices, which may change the picture of the future. In fact, some of these are already on the network, but it's not a lot of it. Okay, power from different sources are sort of intermingled, and what you do, as I said, affects everybody else. So if A sells to B, it'll affect everyone else in the system. And if you've already got a line that's overloaded, and somebody then does something over here, that may be enough to push you over the edge. It also means that everyone who owns a power line can affect prices in the system by perhaps restricting capacity or taking that line offline. What you do affects everywhere else, and this can be used to manipulate prices in your favor. So we've got market monitors like me, you have to watch out for this. Another very odd effect is that if you add a transmission line, it can actually worsen the performance of the system. It can worsen the capacity of the system, how much power you can move through. If I add a fourth line here, but it's a thin line with little capacity, it might become a limiting factor between A and B, and suddenly you could ship 2,000 before, and now you can only ship 1,500.
I don't think you would if you stick to Ohm's laws and Kirchhoff laws. You might with reactive flows.
No, it does.
Ohm's laws and Kirchhoff laws give
Absolutely.
a minimum of the energy losses, don't they?
That's true. In terms of energy losses, that's right. Energy losses are minimized by Kirchhoff's laws, but if you have capacity limitations, you can only put so much current through a line before it overheats and sags, which is what caused the August 2003, what initiated the August 2003 blackout in the US. You have to worry about the capacity of the system. And if, for example, I added a fourth line, but I didn't bother to clear the vegetation under it, it would only be able to take a small amount of current, so you'd have to back off your generation so you don't overload that one line. But that was an excellent point. Okay, so you've got to consider all this in your mathematical models of the physics as well as of the economics. Now, AC load flow is much more complex than what I've just shown. Let's just skip this. It's not really essentially important. But what the Kirchhoff's laws I showed before have to be satisfied in every instant. In an AC power system, we have sinusoidal power. Here in the UK, 50 cycles a second. Every second, it satisfies Kirchhoff's laws. And then something called the AC load flow problem then is, what is that? That's what you're trying to do is calculate the amplitude of the voltage at each location in the network, the angle with respect to all other locations in the network, and that's what that's what causes the load flow. You want to describe likewise the current and so forth. And what you get are some very highly nonlinear equations. Well, it could be highly nonlinear if you highly load the system. However, us economists, yes?
Can I just point out, you said that the reactive current does no, reactive power doesn't do any useful work. But you do need it in the system because it's reactive power that allows you to turn on power stations. Without it, you can't kick in a new power station.
That's interesting. So like for black start, is there no electrical engineer who can help me confirm that?
Planners always want to know how much reactive power they've got in the system so that they can kick in the power station.
That's interesting. I've always thought it was nothing but a headache because This is basically power sloshing back and forth in the network under normal conditions that's causing resistance losses and chewing up capacity. But actually, when you when you black start a unit, you black start it with, you're saying with reactive power. So I stand corrected. I'm getting a head shake from an electrical engineer, but we can talk about that during the break. Okay, what we economists do is linearize this stuff, and it turns out in 98 or 99% of hours, this highly nonlinear system behaves very close to linearly. So we make some assumptions, we get the nice result that the power flow is governed by a set of linear equations. If the power flow is governed by a set of linear equations, we get some nice results in terms of, for example, superposition. We can use impulse response functions, things like that. 15 minutes left. I'm going to go on ahead and just give you some intuition for how these equations behave. So if you take my word for it that except for 1 or 2% of the time when the system is really highly stressed, we can assume linear behavior, we have something called the linearized DC load flow model. So let's look at the way this model might behave on a triangle network. We've got 3 locations where demand and supply might be provided or might appear, and we've got lines connecting them, and let's assume that each of them have reactance equal to 1. By reactance, I mean inductance minus capacitance, or is it the reverse? So if we have the same reactance at all lines, what happens is that, according to Kirchhoff's laws, an injection of power 100 megawatts at A and a withdrawal down here will be split 1/3, 2/3. It's sort of you've heard of the inverse resistance law, that basically power flow between 2 points will be split according to 1 over the resistance. Well, this is analogous to that. So 2/3 of it follows the path of least reactance, and 1/3 follows the one that has twice as much. And this is determined by the equations. If you write down the current law, these are analogies to Kirchhoff's current laws. At every point, flow in has to equal flow out. For example, at C, 33 plus 67 minus 100 equals 0. And then the analogy to the voltage law is that if you go around from A, B, and C, the power flow times the reactance has to add up to 0 by the time you get back to the beginning. You actually have 4 of these equations, of which 3 are linearly independent. You have 3 of these equations linearly independent. You can solve for the 3 flows, and that's how you get that. And because those equations are linear, you triple the inputs, you get triple the outputs. You can take advantage of this proportionality by defining something called power transmission distribution factors. This basically are just coefficients that you calculate ahead of time that tell you how the power is split among the different lines. These are sometimes also called swing factors. So for example, this particular PTDF is the amount of megawatts flowing from J to K if you inject 1 megawatt at M and take out 1 megawatt at N. So for example, if we put in 1 megawatt at A and take out 1 at C, 1/3 of it goes from A to B. And that's what this says. Now on the other hand, if you reversed it, if you put in 1 there and took out 1 at A, you'd get the negative of that. That's a property of this approximation. And this is very useful, as you can imagine, in modeling. Okay, because of the linear system, we also get superposition. We can take this power deal, and we can then ask, well, what if we have another power deal that B sells 50 megawatts to C? What's the total effect on the network? Superposition means we can just add it. That will be the result of those linear equations. And we take advantage of this in our models. So let's do another little exercise. Test your intuition. 3 nodes. We've got a cheap generator up at A. We've got a really costly one here at B. There's no transmission limit except here. That's where we've got a problem, that we have to limit flows to 100 megawatts in either direction. And our demand is 500 here and 400 there. So I think that's just what I said. So the question is, what's the optimal level of operation of each of these two plants? We have to meet this demand of 900. Which plants should be operated? And what are the marginal costs, or what are the Lagrange multipliers, or what are the dual variables at each node? It's the way you economically interpret that. These are the Lagrange multipliers for the constraint that power in has to equal power out at each location. And in this case, it's the marginal cost of 1 more megawatt at a particular node. So turn to your neighbor for a couple minutes, and I'm going to put in some possible answers, and I want you to tell me what the right answer is. So we want the optimal dispatch, and we want the price at each location. So go ahead and start talking, and I'll put down the possible answers.
First, provide the 400 megawatts.
Yeah.
Okay, then you load a generator until the
So which of those answers are right? So continue talking.
I think 250 we can feed because 250.
Okay. Let's take another 15 seconds and then.
Oh, I see.
Okay, does anybody want to volunteer an answer here? How much do you want to generate from A? I tell you what, let's hold off. Let me just show the model that you can use to solve. I'm sure some of you set up this linear program and solved it on your phone, right? Yeah, anybody have Cplex on their phone? Yeah, okay. So to solve this, I need another decision variable, and I'm going to call it Z, which is the net megawatt injection in a node. So if you have more generation than demand, Z is positive, Z is positive. If you have more demand than generation, it's negative. That's what goes into the network and then has to be distributed in your load flow. So compared to the previous model, we're minimizing cost, but now we're summing over all nodes, or what are called buses in electrical engineering jargon. We have a net injection at each point that's Z is equal to generation minus demand at each point. I have no resistance losses here, so these have to add up to 0. Overall, for the network, supply has to equal demand. Oh, capacity constraints. And then here are these PTDFs. I'm taking advantage of a superposition here, that a linear function, an affine function of of Z has to be between the transmission capacity limits. Okay? So I'm sure this is what you solved, right? So we have 1, 2, 3, 4 decision variables. Oh, we don't need a ZC because we don't have generation or demand there. However, I can't calculate. I want the Lagrange multipliers for that because I want to get a price of Z, so I should throw in something in there. If any of you know anything about degeneracy, I'm sure you're going to. I'm not talking about what you do on Friday nights. I'm talking about a mathematical condition called degeneracy in optimization models. We would have that in spades if I threw one in for C there, so we have to do something about it. But that's a footnote. Okay, that's what the model would look like. And so here's a solution. Somebody said 700? Mm-hmm. Yeah, that's the most you can force in up there. And when you have the 2/3, 1/3 split, that gives you, let's see, 700, 400 is eaten up by demand. So 300 flows on the network, of which 1/3 goes through here, and you hit that constraint, leaving B to pick up the slack, having to produce the other 200 there. So your guess was right there. Prices. Well, both of these plants are operating and can vary, so they set the price at their locations. A is going to have a price of 20 because that's the cheap plant. B will have a price of 70 because it's the expensive plant. And then, how many of you guessed this? You don't have to say. The price is -30 here. Anybody guess that? Well, you probably knew if I put down -30, it had to be. Right? I mean, what's going on economically? What's going on economically is if I wanted to bring 1 megawatt to C, so let's say I had a demand of 1 there, where would it come from? Well, it turns out if I put 1 more there, the optimal way to do that is to produce 2 at A, and I can then back off 1 at B. So what happens is 1 of those megawatts at A comes to me, the other one goes to the demand here. By backing off $70 here, costing me only 40, I have a negative price of 30. So we want to pay people to use up energy. And you do see negative prices in real power systems because of these network effects. You can also get negative prices because people want to keep their power plants turned on. They don't want to turn them off at night. There are lots of reasons to get negative prices. But I mean, it's weird. An economist would say, oh, well, the price would have to be somewhere at least equal to the cheapest plant if they didn't know anything about electrical engineering. But in fact, you can get prices that are very, very low, negative thousands, or very, very high, positive thousands. Yes?
Why wouldn't you put a resistor, variable resistor at C, so you have it at V0?
Yeah, just a lot of T heaters. That's a great idea. Well, there's a capital cost to that, which brings us to our next part and last part, which is capacity expansion. You can add power plants, but you could also add resistors, big T heaters. If I'm not mistaken, some nuclear power plants in the US have these things because if they're suddenly cut off from the grid and have to dump power, they have a place to put it. But of course they cost money, and it depends on what the other alternatives are for getting rid of that. Okay, in this last model, we're going to make capacity a decision variable. It was fixed before. So we're not just doing control now, but we're making investments that are going to be long-lived. And it has some sort of cost, which we add to the objective function. So now we're choosing how we control the system and how we design it. And the best combination of those has to satisfy all these constraints. These constraints are the same as before, except now I've moved capacity left-hand side. Oh, I have a new constraint here, reserve margin constraint. Somebody might say you have to have 15% extra capacity, for rainy days, basically, for days that plants go down or whatever. So, in fact, the new government is talking about adequacy mechanisms to pay people just to build power plants to keep them around, even if they don't operate them. So that's an example. So we don't have time to do this, but I was going to ask you to think about what would be the best mix of these things. And it turns out that when you have different types of power plants you could choose from, some are expensive to run but cheap to build. Some are really expensive to build but are cheap to run. It turns out when demand varies, You want a mix of those. You don't build all nuclear plants. You don't build all diesel peaking facilities. You have a mix of things because it's cheaper, for example, to meet the peak with the cheap-to-build plant, even if the fuel bills almost kill you. So we would have worked through this, and we could have calculated some Lagranges and things like that. It's just like before. We have 4 operating variables because we have 2 periods times 2 plants. But now we add the 2 design variables for 6 variables altogether. They said they had 6 blackboards here, but not a 6-dimensional blackboard, so I can't draw the feasible region. 4 capacity constraints as before, the reserve margin constraint. The solution looks like this. You build enough of the expensive capacity that's cheap to run to meet the base demand and use it to meet that. And then you build enough of the diesels or the combustion turbines or whatever to meet the rare peaks, and then some. You have to have a little extra capacity around in case something breaks down. That's the optimal solution. The Lagrange multipliers are kind of interesting. On this constraint, the Lagrange multiplier is basically the capacity cost of that cheap-to-build plant plus its running cost, basically. Here, it's a little bit different. If I have 1 more megawatt demand, I have to build some more coal capacity so that the Lagrange multiplier price will equal that cost, minus the fuel savings, because if I have some more coal here, I can save some gas there. So the marginal cost here is not just the cost of a coal plant. Okay, my last slide, because I know it's break time, right? Don't tell me I have another 15 minutes, please.
No, you haven't.
Okay, so my last slide. We haven't done anything stochastically. In fact, the future is highly uncertain. We don't know how much. Is the government really going to adhere to its target of 20% wind, roughly, by 2020? Do they have the backbone or whatever piece of the anatomy it takes to do that? What's going to happen to the future cost of nuclear plants? I mean, the world is highly uncertain. Look what happened to Obama's climate bill. He makes a concession. Republicans say, please, we need a couple of Republican votes. And the concession was to allow more offshore oil drilling. What happens a month later? Okay, the world is full of these things, and you need to plan plan with those in mind, or you may commit yourself to a course you'll really regret later. So imagine that you have a bunch of scenarios of things that could happen with the probabilities. What I want to do in this model is consider decisions I have to make today with my eyes covered, I don't know the future, and then after the curtain is drawn back and I know what happens, how do I then operate or adjust the system after that? It's called a 2-stage model, or a model with recourse. So there are here and now decisions with the current drawn across, the veil drawn across, we can't see the future. We just know that there are some things, different things that could happen. And these here and now decisions are things like, do we invest in a nuclear plant now or a transmission line? Then there are wait and see choices. Go into the future, we now know what's happened. Oh my goodness, demand has really grown. Everybody's got electric cars, we've got to build some more power plants quickly. That means diesels or something. So short-term lead plans, how you operate. And so I partition the set of decision variables into here and now versus wait and see. And our little optimization problem is, if we're minimizing cost, we're going to minimize the cost of here and now plus the cost. Well, actually, I should have x1s in there as well, but that's okay. The future cost weighted by the probability of the scenarios, and then you have a set of constraints that there are constraints on decisions you make now, where you can build the nukes, for example, and there are constraints in the future. For example, under scenario number 3, if you didn't build a nuclear plant, x1, you can't run it. So there are constraints that couple those two. Math program with recourse. So let's take our 10,000 variable problem and now consider 100 scenarios, 10,000 variables now becomes 1,000,000. And so these problems get very big, which is really fun for the computational folks. It's break time. I've run over. Thank you for your patience. And you'll see Danny up next.
Ben, thank you very much for fascinating. Any quick questions before we have have a break. We've got time for one or two.
It's interesting on the screen. So, in the parallel, do they? I mean, right there, this is all risk neutral, and so it might be a mean profit is fantastic, but the variance is infinite, and
That's right.
so nobody will go into that business.
Oh,
you have that thought.
that's a really good point. I'm assuming risk neutrality here, that all you care about is the average level. But of course, if you've got a house by a river, you don't care about the average level of the river. You might care about the extremes when you're one day per year that you're underwater. So, and the decisions may be very different, and this is actually a real problem for users of policy models like myself. We use models like that have 1 million variables, but we know that in fact, people in the real world are very concerned about risk and they make very different sorts of decisions, but our models don't capture that. So is there some way we can improve these models, still have all the rich texture we want about transmission lines and so forth, and capture risk aversion? And that's an active area of research, and it's actually something that Danny's working on. So excellent question.
Following on from that, just a comment following on from that. On Thursday there'll be a presentation by someone from British Department for Energy and Climate Change on precisely how you build economic projection models considering different types of risk aversion and future uncertainty.
Okay, nice link.
Okay. Any other questions for the break? I think there'll be further opportunity for questions later because I think Ben will be back again later in the afternoon.
Yes.
Yeah. Okay. Other questions? Okay. So we are resuming now at 3:45. This tea and coffee outside. Again, Ben, thank you very much.
You are welcome.
Indeed.
Is this door open? No.